some of the evidence we have. Oh, okay, so it's being recorded now. Okay, good. Okay, so as many of you know, HCF, Hauser-Chomsky-Fitch, calls recursion is a core property that defines the two senses of the faculty of language. Okay, so it's we have the faculty of language, the broad sense, which actually includes everything, the internal computational system, the FLN, and the interface, the sensory motor and the conceptual intentional systems. Okay, but FLN, the faculty of language narrow sense, is just the abstract linguistic computational system alone. Okay, independent of the other system, independent of sensory motor and conceptual intentional. But the FLN interacts with these systems through the interfaces. Okay, so the claim here is that FLN is uniquely human. Okay, so it's not found in other non-human animals. Okay, and the claim also is that it comprises only, sometimes you say mostly, or the core computational mechanisms of recursion. Okay, as they appear in narrow syntax and the mapping to the interfaces. Okay, so this is something that we'll probably have to unpack a little bit, but since it's uniquely human, the other claim is that it has recently evolved and it's unique to our species. Okay. On the other hand, the peripheral components of FLB, sensory, motor, conceptual, intentional, are shared with other non-human animals in more or less the same form as they exist in humans. So there's some kind of continuity, evolutionary continuity, with differences in quantity rather than kind. Okay. But what is unique to our species, quite specific, is the FLN. Okay, and it includes the internal operations as well as its interface with the other organism internal systems. Okay, so at least this adoption, okay, of Hauser-Chomsky and Fitch of the FLN. Although it could be said that it's quite syntactocentric, it doesn't exclude the interface systems. So for that I mean phonology and semantics as the interfaces with the organism internal system. So we there's a claim that phonology is part of the faculty of language narrow sense, okay, although it's been discussed and debated, of course. Okay, so the other thing is that the FLN may be the kind of optimal solution to the problem, of the interfaces. Yeah. Okay, so first of all, let's talk a little bit about recursion. Okay. This is, it may seem strange for some, but actually it's difficult to find a definite consensus about the definition of recursion, but it converges in that recursion is a process that consists of defining the value of a function by using other values of the same function. This is a rather broad definition, and it allows for many phenomena to be included in recursion, which probably some people may argue it's not. But we'll talk about that. So, a common example in mathematics is the factorial function. Okay, so as most of you know, the factorial, okay, of a number is the product of that number by each one of its predecessors. Okay, so a factorial of 4 is 4 times 3 times 2 times 1. Okay, factorial of 6, 6 times 5 times etc. Yeah, so this can be defined recursively. Okay, this can be defined recursively, and typically that requires two kinds of statements. Okay, one which is the base case. Okay, so we can say, okay, we define factorial of 0 as 1. Okay, and then what actually makes this a recursive defined function is the inductive step. Okay, the inductive step, it says the factorial of n equals n times factorial of n minus 1. Okay, so so you see that the factorial function is in both sides of the equation. So we can say that in the inductive step, the factorial function is defined by calling itself. Okay, by calling itself. So it's this is typically of recursive definitions. Okay, so we actually see here an example, okay, of a recursive definition of factorial. If you see that the table here at the left, okay, where we see the factorial of 4 is 4 times factorial 3. Okay, but the interesting thing is that there's nothing inherently recursive about the factorial function. Okay, so factorial function can be defined also iteratively. Okay, which may or may not be considered a recursive a process, but let's see, we'll talk about it. Okay, so some examples of recursive definitions or recursive functions they call actually. We have first what they're called the initial functions. Okay, so in functions like the successor function, okay, the zero function, the projection function, and actually they can be composed in order to form other functions. Okay, like a predecessor function or constant function. Okay, so these are in functions that can be the very simple function that can be defined recursively. Okay, Olifredi and Cooper actually add to types of recursion the iteration. Okay, as the simplest type of recursion, and this is something that not everybody agrees that that iteration is a type of recursion, but because of some fundamental difference or differences that can be esteemed as fundamental, but there's definitely a calling of the procedure, okay, when we iterate, okay, but normally, okay, the difference is in calling the function versus calling the variable, and I think that that's the difference between recursion and iteration. But you could say that both are examples of recurrent definitions. Okay, but let's say that iteration may be regarded as some simple type of recursion. Okay. We also have, what will be fully fleshed recursive definitions of primitive recursion, which actually we see the two kind of statements: the base case and the recursive or inductive step. Okay, in some function like the predecessor function. Okay, so the function that says what's the number before, right? the natural number before n. Okay, okay. So primitive recursion definitions can have parameters. Okay, and the classic example is the towers of Hanoi, or sometimes called towers of drama, and this is a problem that is probably common for students in computer science. For those of you who are not that familiar, it's like how the procedure of moving all the disks in the first pole A, and moving them to pole C, but there's some constraints, okay, and is that you can only move one disk at a time, okay, and you cannot have a bigger disk on top of a smaller one. Okay, so so those are that's why I call that, those are the parameters of this procedure. Okay, and this can actually be defined recursively also. So it's recursion with parameters. Okay. We have course of values recursion, okay, and it's like primitive recursion, but it allows for more than one value of the previous argument. And classical examples, the Fibonacci sequence, okay, which is recursively defined using the basic steps, okay, and the recursive step, which, as you see, uses two callings of the Fibonacci function. Okay? So you may know the Fibonacci sequence is the sequence of numbers that you get by adding the previous two. Okay, so we define the first two Fibonacci numbers, 1 and 1. Okay, the next would be the 1 plus 1. Okay, and that it gives us 2. So the next Fibonacci number would be 1 plus 2. That's 3. And the next Fibonacci 5 is 2 plus 3, and so on and so forth. Okay. Okay. And of course, there are other more complex forms of or types of recursion, okay, like double recursion and minimization of M recursion. But we are actually, just wanted to mention, but not talking about that. Okay, so we should not forget, okay, that this definition of a recursive definition as the way of defining a function by specifying each of its values in terms of previously defined values. Okay. So here, okay, we see the definition by induction is actually the original sense of recursion in mathematics. Okay, and one one typical example of definition by induction in linguistics is given by Chomsky in the minimalist program when he defines syntactic objects recursively. Okay, so syntactic objects are lexical items, okay, or the set gamma and the set alpha and beta, where alpha and beta are objects and gamma is the label of K. Okay? So we have a definition by induction here. So a general and central property of algorithms and generative systems. Okay. Production systems of rewriting rules also contain recursion as a central property, okay? But not simply in those specific cases in which the same symbols appears on the left and right hand side of the rewrite rules, which are the typical cases, or the telltale of a recursive rule. Like we have S is rewrite as A S B, the typical rewrite rule for center embedding, okay, where you see the same symbol at both sides of the rule. But sometimes there is recursion in the interaction of rules, okay? So, and that's typical in production systems of rewriting rules. So it's, we can see that in syntax, for example, the rules for clauses, for subordinate clauses, okay? Which we can see as recursive, but actually it's a combination of the application of rules in specific order that give us the recursive structure. Okay. So yeah, just trying to pace myself because I think I probably have too many slides, so I'm just going to move on a little bit. Okay, so another meaning of recursion, okay, see, it's as a property of computational processes or implementations, okay? So we may say that a process, a computational process is recursive, okay? when the operation calls itself, creating chains of deferred operations. And I think that's a pretty standard definition for recursive process, okay? And it's usefully contrasted with iterative processes, okay? Where an operation reapplies in succession, okay? So there's a, the difference we can see between recursion and iteration, okay? However, okay, all recursive relations can be reduced to recurrence or iterative relations, okay? So, they're extensionally, so you can redefine a recursive process iteratively, extensionally, okay? So while both types of processes keep something in memory, okay, recursive processes, okay, keep deferred operations rather than just variables, and that actually exerts a bigger load, a bigger memory load. Okay, so you can see that with very simple computer programs for calculating Fibonacci numbers, for example, or factorial, or the factorial class. If you use a recursive if you define the process recursively, it actually is going to take more time than to give you an answer, okay, than when your program uses an iterative procedure, okay. So and that's a little programming experiment that you can do, okay. So okay, so it's recursion can be used to describe procedures, but it can actually be a property of structures, okay? And many times we hear about a recursive structure, okay? A recursive data structure, and that is it's not actually used originally in the mathematical sense of recursion. It's not used for structures, but it's common, to see recursion or recursive as a property of structures on top of a property of procedures. Okay, so recursive data structures are defined as partially composed objects or classes that are partially composed of smaller or simpler instances of the same data structure. Okay, so comes to mind, something like fractals, okay, or trees, or syntactic trees, okay, where it's a smaller or a smaller part of the tree, it's still a tree. It's an instance of the same data structure. Okay, so trees within trees, okay, which are familiar to generative grammar. Okay. But the important thing here, okay, when we say that that a recursive data structure is an X within an X, is that what are we actually what is the nature of that X? Okay, so when you say X within an X, okay, what are we talking about? What is X? Okay, so in terms of phonology, for example, we say again, we have a syllable within a syllable. Okay, if X is a syllable, okay, we have syllables within syllables. Well, some may answer no. Some may answer yes. That's debatable, but that's it's important to keep in mind what is that we are taking as the X in the X within an X. Okay, so the general recursive property of generative systems, okay, pertains to the study of cognitive structures and capacities, okay, in terms of the abstract mappings between inputs and outputs and the formal properties deriving therefrom, okay, that is to the computational level of explanation, okay, and the study of faculties as understood by Chomsky. This is a claim by David Lobina, okay, about general recursive properties of generative systems, okay. So it's there's here the distinction between levels of explanation. Okay, so the on one hand the computational level of explanation. Okay, on the other hand the algorithmic level of explanation that will focus on operations, okay, and processing modules, okay, and those of you familiar with Marr, is the lowest level, is the hardware of or implementation level, okay. So this distinction is going to be quite useful in assessing, probably the value of the evidence that it's given by artificial grammar learning experiments. In terms of this results are actually giving us information about one of these levels. Okay, so and that's why it's good to have this in mind. Okay, so in their paper, Watermull and et al. They present the thesis of recursion, okay, based on, or this claim to be based on standard mathematical definition of recursion as understood by Gödel, okay, and they define there are three criteria properties of recursion, okay, computability, definition by induction, and mathematical induction, okay, and each of these criteria properties is going to correlate, okay, to a property of the system of the presumably recursive system. Okay, so by computability, okay, Watermull takes that rules are defined in intention rather than in extension, rather than lists in extension. Okay, and this is interesting because the relation between computability and intentionality, okay, we have the non-arbitrary set generated by a recursive function need not be represented as an output. So to recursively generate a set is not to produce it. Okay, so and this is key for rules defined intentionally and not extensionally. Okay, so since the function is defined in intention, it specifies the conditions some object would need to satisfy to be subsumed in the set. Okay, so it's even possible that not such objects are presented. Okay, and that's so that will be any rule in intention that will have that will produce no object. Okay. And the generative function, it will be a finite conditional branching program, determines a potentially infinite set of structural expression that could but need not be enumerated. Okay, so here, okay, the I language, E language competence performance distinction is fundamental to understanding the nature of faculty of language narrow. Okay, remember we understand the I language as the intentional internal, okay, part of the grammar. Okay, so and in the case of definition by induction, okay, which is the second property that that Watermull et al. Define here. Okay, the claim is that that has the consequence that rules strongly generate structure. Okay, so and they use a quote by Gödel, okay, which may or may not actually justify this claim by Watermull, okay, that the definition by induction requires, that the system that the rule strongly generates structure. Okay, remember that strong generation refers to structure versus weak generation that refers to production of just strings with no internal structure. Okay. So the claim by Watermull is that the definition by induction, that is this criteria property of recursion, requires the generation, the strong generation of structure, and not just strings. Okay. Okay, so I'm going to keep some of this. Okay. I'm sorry, but okay, yeah, just wanted to move a little faster, okay. And the third criterial property, which is mathematical induction, okay, as it refers that the rules of the system of the recursive setting has to be principal, okay, and potentially unbounded, okay. Rules for the principal and potentially unbounded expansion of strongly generated structure, okay. So the critical fact, I'm sorry, okay? The critical factors to proper understanding mathematical induction is the infinite generation, okay? Potentially unbounded production, okay? And recursive intentions, okay? So this is very important because infinite generation means that the recursive function may generate an infinite set, okay? But may only produce a finite output because of arbitrary constraints. Okay? So infinite generation does not equate to infinite production. Okay? So finite brains running in finite time literally do generate infinite sets. Okay, and generate in this sense, not producing sets. Okay, that of course will be impossible. Okay, but intentionally they're generating, okay, infinite sets. Okay, so in terms of the other criteria is the potentially unbounded production. Okay, so because the range of recursive function is by definition non-arbitrary, any arbitrary limited output can be explained in a principal manner. Okay, so the unboundedness is principal. Okay, but if there are limitations or constraints to the production, that will have to be stipulated. Okay. And the third is the recursive intentions, okay? That the representation or extension of the set generated is immaterial to the form or intention of its generation, okay? So given that recursiveness is a property of the procedure applicable to any input rather than a property of the potential output, equation recursion with syntactic embedding is simply a fallacy. This is this is actually a conclusion by Warmo. Okay, so and actually this equation of syntactic embedding with recursiveness, it's something very common in the literature, and it's probably most probably what sets the claims by Dan Everett about the Piraha don't have recursion because there's apparently no instance of embedding, syntactic embedding. Okay, but recursion is not necessarily self-embedding. Okay, so actually the original Chomsky's use of self-embedding is for strings. Okay, it's not in phrase structural terms. Okay, and recursion is more general than just self-embedding. Okay, so the natural numbers also rely on recursion. Okay, although possibly with finite state grammar. Okay, so we don't even need all the power of a context-free grammar to see examples of recursive procedures. Okay, and actually the natural numbers may be generated recursively. Okay, but we would not say that 3 is embedded in 4, for example. Okay, although we can generate all the natural numbers, okay, with a successor function, which is actually one of the initial or primitive functions. Okay, so to equate recursion, which is a property of the generative procedure, okay, with possible properties of its potential output is can be seen as a mathematical error. Okay, so properties of the procedure, okay, and properties of the output are not the same. Okay, so embedding is, of course, there's as a computational capacity is not synonymous with recursion. Okay, and actually that was not part of the original claim for recursion in the Hauser et al. Hauser, Chomsky, Fitch. Okay. So another thing that recursion is not, okay, or does not, okay, is that recursion does not entail unlimited depth of embedding. Okay. So any limitations on depth of embedding, okay, in structures that FLN does generate can only be arbitrary. Okay, arbitrary with arbitrary with respect to the generative function. Okay, so and this is the limit, and that is because of several factors. It could be limitations at the implementational level. In the typical example would be the classical examples of self-embedding, like the cat, the cat that the mouse, the cat, the mouse, the cat, the mouse, the cat catch die. Yeah? So we can have one level of self-embedding, okay? But if we try to go beyond that, it's kind of difficult to process. It will be a perfectly fine, a perfectly grammatical sentence, but it's difficult to process. Okay? So, so that would be probably because of limitations at the implementational level, okay, the memory limitations. It could be limitations at the algorithmic level, and that probably what may happen in the case of Piraha or other languages like Kayara did. Yeah. But they anyway, any of those limitations is external, okay, to the computational system. So computational system is perfectly fine, generating unlimited depth of embedding, but limitations, but there will be limitations in specific languages. Okay, so unboundedness is a property of the generative competence and not its application in performance. Okay, and so that's an important thing to remind. So another thing that recursion is not, okay, well, not recursion, but boundedness is not principal but arbitrary, right? The same reason that we just were mentioned, okay? Even alleged grammars that produce maximum phrases according to certain stipulations, okay, like the verbs, lexical frame plus like Everett claims for Piraha, for example. Okay, so the alleged grammars that produce maximum phrase according to certain stipulations are recursive. Okay, so recursive. Remember the three criteria. Okay, the computability. Okay, definition by induction, and mathematical induction. Okay, so so even these grammars like Piraha, okay, are recursive by these criteria. Okay, so is demonstrably computable. Okay, so I mean that the set of possibly phrases in Piraha, even in Piraha, is not arbitrary. Okay, and even if finite, yeah, it contains too many members to be listed as a lookup table. Okay, so it must be generated by the finitary recursive procedure. Okay, so it is that the grammar can be defined by induction. Okay, so the outputs as recursed as inputs to strongly generate structured expressions. Okay, remember that equation, that equating in Watermole definition by induction with hierarchical structure. Okay, and the function is mathematically inductive. Okay, is unbounded in principle. Okay, so and that unboundedness will emerge if the arbitrary restrictions were relaxed. Okay, so by these three criteria, okay, even languages like Piraha, contra whatever claims can be they're not exception because they're recursive. Okay, so. Okay, so I think pretty much that's the gist with this thing. Okay, so so now the second part of the two parts here in this talk. The second part is the phonology. Oh wow, I think that time is moving very fast. Anyway, okay. So what is the place of phonology within faculty of language? Okay. Well, common wisdom is that phonology is neither recursive and probably not even part of FLN. Okay. So a probable argument. Okay. This is not the structure of the argument for getting to that conclusion, but we know phonology is regular, or at least we highly suspect that phonology is regular, or probably even subregular. Okay, but not finite. Okay, so there's a claim that phonological structures are not hierarchical. Okay, and Bill is one of the proponents here, and the phonology lacks recursion. Okay, that's actually that's also a claim like in Pinker and Jack and Dove and Bill Sardi as well. Okay, so phonology lies outside FLN. It doesn't have the at least that seems to be the structure of the argument in Sardi's paper. So, but perhaps he may be willing to talk a little bit about that, in the question session. Okay, so only syntax seems to lie within FLN, and all other systems, including phonology and perhaps semantics, belong to FLB. Okay, Fitch also said that phonology is shared with other species, and that he actually postulated the phonology continuity hypothesis. Okay, so actually, I'm going to be very sketchy with this because to go to the part that actually it was probably more medular about the artificial grammar experiments and neuroscience. So this is just some evidence, some of the claims that phonology is regular, may even be subregular. Okay, so I'm just going to move fast here. Okay, but phonology is not finite, and that's this is I think this is very important. Okay, because there's it doesn't seem to be a bound. Okay, of how many how many syllables a word may have in a language. Okay, so there's an unboundedness. Okay, in phonological structure, and probably it could be an infinite number, potentially an infinite number of prosodic words in a language. Okay, so of course there are going to be limitations of memory, okay, all the limitations of the other systems, but the phonology may generate an infinite number of structures. Okay. So we're going to subscribe to the claim that phonology is not finite. Okay. So, okay. Let me see if I can actually go probably faster this way. Okay. I'm sorry. This time goes much faster than I expected. Okay, yeah. So, and we also have the claims that phonological structure is hierarchical or not hierarchical, but I'm going to skip that to go to, let's see. Okay, I'm sorry about this, but actually be okay. Huh. Okay, I just want to move to the AGL part, but I'm having a little problem with this. Sorry about this. Oh, okay, I think I found it. Oops. Okay, I guess this is it. Okay. 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 So there, artificial grammar language or artificial grammar learning experiments actually may, or they claim to throw some light over this question of recursiveness, okay, in language in general, but it can actually be applied to phonology in particular, okay. So, well, things we know, okay, we know that language processing, it is supported or subserved by a specific network in the left hemisphere, okay? And there are claims that the computation merge has been located in a subpart of the Broca's area, okay? So, and the claim is that this part processes hierarchical structure. Okay, so so the question would be, if the processing of phonological objects or in tasks involving phonological rules, if the Broca's area activated, okay, if the claim is true that Broca's area actually has to do with the processing of hierarchical structure, that might be an indication of the biological implementation of a recursive process for phonology. Okay, so there are 3 experiments by the group of by the research group of Friederici, which may throw some light. Okay, and the first one is the 2006 experiment with finite state grammar versus what they call phrase structure grammar, which is actually like something like a context-free grammar. Okay, and in this experiment, the subjects were actually taught sequences of syllables. Okay, and they were taught sequences that were grammatical and then incorrect or agrammatical sequences. Okay, and then they had to in the experiment they had to evaluate words. We can call this words or sentences to see if they were grammatical according to the to the grammar that they were supposed to acquire. Okay, so rules were not taught explicitly. Okay, they were just they were given inputs, and they had to generate the rule. Okay, or they have to create the rule. And the thing here, for the what they used was for structures like the finite state structure A B A B A B. They used for the class A was I don't know if you can see that here. There are syllables containing vowels I or E. Okay, so de, gi, le, ri, se. So they're all category A. Okay, category B would be the syllables with O or U. Okay, so so in this language that we're taught, words like de, bo, gi, fo, okay, or de, bo, gito were actually grammatical, okay, because they were sequences of A, B, okay, but something like de, bo, gi, le, okay, was not, okay, because they were supposed to be the fourth syllable here was supposed to have O or U. Okay, so it should be supposed to be class B, not class A. Okay? In the case of the context-free language, okay, there will be then nested dependencies. So it will be A, B, B, okay, like ti, le, mo, gu. Yeah? So ti, le, mo, de, okay, would be ungrammatical, okay, because there's it violates the A, N, B, N phrase structure grammar. So what actually it was found here was that the in processing the finite state grammar, okay, in processing the phrase structure grammar, the Broca's area was activated, and the network that is identified as subservient of hierarchical structure processing was activated. But in the processing the finite state grammar, the Broca's area was not activated. Okay, and that network was not activated either. Okay, so it seems that when they were when phonological or structures, okay, were processed according to a phrase structure grammar, it seems that the areas that subserve hierarchical processing were actually activated. This experiment has some flaws. I think it's well, I think it's about time. Okay, yeah. Okay, Charles, I think it's I'm
Well, you know, why don't you take a few minutes to wrap up, and after Jane's talk, we'll have extra time for questions at the very end.
Okay, good. Yeah. So I had other experiments here, but I'm not going to go with that. So the findings, okay, is they seem to support the claim that that there is processing in the areas that subserve hierarchical structure. Okay. But actually, okay, that area, okay, that specific area was sometimes in other experiments was involved in processing so just simple linear grammars. Okay, so it's the evidence is not ironclad. Okay, so that is one problem. Okay, also, okay, some caveats is remembering the discussion that the distinction between the different levels of explanation is that these neuroimaging studies cannot actually tell us anything about the computational mechanisms. Okay, and that is a critique that Lobina has for this type of experiments. Okay, so let me see. Okay, so can we say, okay, where in the brain is phonology? Okay, so the AGL neuroimaging are most probably showing the loci structural process, okay, rather than making real claims about recursion of the structure or the structural complexity of linguistic representation. So there's a difference between structure and recursion. Okay? Remember the difference between the procedure versus the object. Okay. So the studies may still throw some light about the way phonological structures are parsed if they can show what brain pathways are more activated during tasks involving certain toy phonological rules. Okay. So then, okay, is phonology recursive? Well, regular grammars can generate strings, okay, to which a hierarchical representation may be assigned. Okay. And prosodic constituency presents a strong case for the hierarchically structured representation of phonological objects. Okay, and also remember that phonological structures seem to be potentially unbounded and to conform to perhaps an infinite set. Okay, or at least too large to be defined extensionally. Okay, and that will require a recursively enumerable generative procedure. Okay, so claims that phonology may actually be recursive according to the criteria that we defined before. Okay, and there is a place of phonology within the FLN. Okay, in the interfaces to the other systems. Okay, so that's it. I guess I'm consuming all my time, but see, we any questions that you have, we can have it after the other presentation. Okay, so thank you very much.
Thank you. Actually, Hilton, we have 5 minutes now.
Okay, good. Okay, okay.
How about anybody have something right away?
Yeah.
You're up, Bill. Go ahead.
Thank you. Yeah, I'll just briefly say that I think that the Friederici syntaxes in Broca's area, I think you need to look very carefully at what Greg Hickok has been doing. And I'll just briefly mention one thing, which is that damage to Broca's area generally doesn't affect the receptive ability of language users. And so the way that Greg, through this dual root model that he developed with David Puppel, thinks about it is that really Broca's area is more concerned with the assemblage of items for the purposes of production rather than perception. So the brain is a very complicated place, and it looks like there's hierarchical processing that certainly goes on in posterior temporal lobe that is related to the frontal areas. So I think that this is a very difficult question to assess with brain imaging, but I applaud you for trying.
Yes, actually, I don't think it actually can be answered by that, at least with the technology we have now. And as you said, Broca's area may actually have to do with hierarchical processing, not even only in language, but it's in processing music. In other domains, it actually activates, and that network that actually activates with the PSTG, the posterior STG. So
let me just interject here that at DeHaan's conference that was going on a couple days ago, the very last talk by Stan DeHaan, he gives a number of dissociations between these abilities that people like to lump together. So arithmetic versus language, language versus music, music versus geometry. And they can all have dissociations neurally. So even if there are, copied and modified circuits that are located in approximately the same areas, that doesn't mean they're the same circuits.
Exactly.
So, I think that the lesion dissociation evidence is very important here.
Yeah. And as you said, the same area may be active in a different network. Okay, so it's Broca's activation with language, the network that activates is different than when Broca's area is activated with music. It's the different networks. So probably instead of that's why there's been the change. Instead of talking of areas of the brain, it's talking about networks. That's actually much more accurate. Yeah, you're absolutely right.
Okay, Tobias, how about a quick question?
Yeah. In syntax, the recursion, or whatever people call recursion, I don't want to go into what you have debated in your talk. So what people call recursion is a consequence of concatenation. So you go fetch items from long-term memory and you glue them together, and that is internal or external merge, and that is as far as I can see, the only source of recursion, of what people call recursion in syntax. So in phonology, phonology doesn't concatenate anything. I think that's consensual, and so there couldn't be any recursion in phonology in the sense that syntacticians have. What do you think?
Well, it probably depends on how we define the domain of phonology. It's kind of there may be recursion in morphology, but not in phonology. Sure. But probably the boundaries are not are kind of fluid.
Well, morphology does fetch things in it's a syntax of small items. If you believe in that morphology is different, but it doesn't matter. It does concatenate. What do you think of the argument that if there is no concatenation, there couldn't be any recursion in the syntactic sense?
If there's no concatenation, but concatenation will produce linear structure or flat structures. So if you're not equating concatenation with merge.
Merge is the operation that concatenates, isn't it?
Yeah, but it actually it creates a structure. Not only a string, but it has a strong generative capacity.
Yeah, sure. But okay. Without there would be no recursion. What people call recursion in syntax wouldn't exist if there were no concatenation.
Well, I would use concatenation, different from merge, but your claim is that it's basically the same operation.
Well, I try to define it. If you go fetch things in long-term memory and you glue that together with whatever operation, right? This is the only source of what people call recursion in syntax.
Yeah, but when you glue two things, okay, and then but you can have concatenation without recursion.
Yeah, sure. But that's true. Of course, you can concatenate without doing recursion. But my proposition is that what in syntax, in the specific case of syntax, that we compare phonology to, right? Because that's what we compare phonology to. In the specific case of syntax, the only source of what people call recursion is concatenation, which happens to be recursive in syntax.
Okay, I think we should stop there.
Okay.
And we'll take thanks again, Hilton, and we can come back to this in the larger discussion.
Okay.
So,
yes, I'm going to go back to that.
A 5-minute break, and James, you just want to get your slides up. Is it working? Or maybe Hilton, you need to stop.
Yes, I need to stop.
Okay.
Yeah, exactly. Okay. Yeah.
Oops. And I need to stop the video. Oops.